What's up? Today we are talking about linear functions. Linear functions, a math term that might sound intimidating at first, but trust me, is really not so bad, and dare I even say fun. Let's get to it by starting off with a real example. I feel like that might be the best way to approach this. So let's pretend I have a job as a typist. I am actually a pretty fast typer. Not super, super fast, but, fairly fast. Let's say I get paid, oops, my pen is off. Let's say I get paid $20 an hour. $20 per hour that I type. I don't know what I'm typing, but that's my job. Let's pretend. I wonder if I would like a job typing, but anyway. Now, this is actually an example of a linear function. And one key thing is to notice is that one thing depends on something else when we are thinking about linear functions. So in this case, the amount of money I earn depends on how much I type. Actually, I should write depends on hours I type. So money depends on hours. And if you're not sure about what depends on what, you can always say, well, you could flip it around. Well, does money depend on hours I type, or do the number of hours I type, does that depend on the money? And then it'll usually make sense to you. Now, my students, we don't have them determine what depends on what, but I think it's helpful in math to just understand that conceptually. Why? Because with linear functions, we have something that is called a dependent variable. This might sound familiar to you, a dependent variable. And we have something called an independent variable. One depends on the other. X denotes the independent variable in linear functions, and Y denotes the dependent variable. And one way to know which one is the dependent variable is that there is the word depend right at the beginning of the word dependent. So that usually helps. And so when we are thinking about this example, one variable depends on the other. And in this case, the amount of money depends on the number of hours I type. So Y is the amount of money. And, oh, whoops, I made a mistake here. That's not supposed to be that. That's supposed to be equal sign, hours. And Y depends on X. And we usually have a table that looks like this. So and then we can have examples. If I type for 1 hour, I get $20. Woohoo! If I type for 2 hours, I get, I don't mean to change the color of that. 2 hours is 40. I accidentally changed the colors of this, and I did not mean to. Let's go back to the original. If I type, why is it doing that? There we go. If I type for 3 hours, I get, oh, it's still shaded, isn't it? Oh, well. I get $60. And so now we see a pattern, and we see that every single time, oh, I see what happened. Every single time I type, for each hour, I get $20 more. And if you remember what the constant of proportionality is, the rate of change, you can see that it's 20. Anyway, I don't want to confuse you too much. This language here is from a reference I gave my students. And the way that we explain it is that a linear function is a relationship between two sets of variables where the rate of change between the variables is constant. So what that means is in this situation with the typing, the rate of change is $20 or 20. It doesn't mean that so what that means is that if I type for 1 hour and I make $20, it would not be the case that I type for $2, I suddenly make $100, because that would be that would not represent a proportional relationship or a constant rate of change. So you can think of the word constant as meaning the same. In real life, there are so many examples of linear functions. We talked about one just now, a job where a person gets paid at a constant rate or wage for each hour worked, or it could be for each day worked, for each month worked. Miles per hour of a car, that is a linear function. The cost of internet service each month. I pay a lot for internet service, and for each additional month, I pay a constant rate that is more. So when you want to think about it in terms of X and Y, the cost depends on the number of months. So cost is Y, months is X. Earning a regular allowance. Some kids are lucky enough to earn an allowance, and it could be by week or by month. I am a cat mom, so I have cats and generally feed them twice a day. Some people do more, some people do less, and so much more. I'm going to erase this writing that I had before. Oh, I have all this writing that I did before. Let me erase it all. Don't want to confuse you guys. So this question is from a worksheet I gave my students, and it is a linear function question. And I think the best way to learn about linear functions is to solve problems about them with real life examples. And here's a real life example. Shani is a clothing designer, and for each shirt she designs, she sews on 2 buttons. So we see here she sews on 2 buttons, meaning here's one shirt. So for that one shirt, she would sew 2 buttons on, which means for 2 shirts, she would sew on 4 buttons, and for 3 shirts, she would sew on 6 buttons. We have a constant rate of change, which is 2. So it's not like one shirt has 2 buttons and the other one has 10. It's just a constant. Each shirt has 2 buttons. And so we've got a proportional relationship here and a linear function that we can plot on a graph. Let's do it. Now, the way to plot this on a coordinate plane, which we have here, is we use something called ordered pairs. Ordered pairs, which is, again, a math term that might sound more complicated than it really is. And all it means is that we plot X and then we plot Y, and we write it in this format, X then Y. So it would mean in this case, we would plot 1 and 2, and then we would plot 2 and 4, etc. Let's do it. Let's use purple. I like purple. So we've got 1 and 2. We find 1 on the x-axis and then 2. So there we've got 1, 2. Then we've got 2, 4, and then we're going to do 3, 6. So there we've got our points from our table there. And now this is the cool part. We can actually, I'm not very good at drawing lines, but I'm terrible at drawing lines, but we can actually draw a line through it. I'm going to draw. Now my line has to go, it's a terrible line, but my line has to go through the origin here at 0, 0, because this is a proportional relationship, meaning if there are 0 shirts, there are 0 buttons. And so we want it to go through the origin. And you might say to yourself, well, why do I need to see this on a coordinate plane? Like, what is I've got the table here. Why do I need to see it on this graph? And the truth is that right now we are dealing with, a simple situation. But let's say you are a giant business. You own a major clothing company with not just thousands, but millions of customers. And you want to know how many buttons to order. So you're thinking about it in the term of every 100,000 customers. Well, when we have this plotted on a line, and computers can do this readily, you can see that line go really, really, really far, and you can find points that go all the way up to, let's say, 100,000 or way higher, and then you would see that it matches with, 200,000. And way, way, way higher. It'll go up to 1 million. It might be a number like 1,250,000. And then you can see, the points. And so having things in a visual format can be very, very helpful. There's one other way that it's helpful, and I know I didn't draw the best line here. A linear function is always a straight line, even though mine's not perfectly straight because I am a terrible line drawer. But if the line looked like that, you can see it's a steeper line. The steeper the line, the faster the rate of y changes with x. And so you can actually have algorithms that show what happens at different rates of change. And I don't want to confuse you too much about it, but that's one of the ways that plotting the line on the coordinate plane is helpful. And again, don't want to confuse you too much. Let's move on to the next question. Aria is a chef. She's making salads for a big event. Each salad will have 2 chopped strawberries. Now this one is a little more complicated because as you can see in the table, I don't have the number 1. And here it says each salad. So that each salad means the number 1. And we've got 2 chopped strawberries for every 1 salad. So I have to use my powers of deduction to realize that the rate of change is 2, which means for 5 salads, I've got 10 chopped strawberries. And for 10 salads, I've got 20 chopped strawberries, and so on. And now let's plot it and see what it looks like as a line. Let's do the color green. So we've got 5 and 10, 10 and 20, and 15 and 30. This line looks like a lot like the last one, huh? Probably because the rate of change is the same. Oh my gosh, I can't even deal with my own line. Let's try that again. Oh, guys, I wish I was better at drawing lines, but you're going to have to bear with me because I am just not that good at it. It is, well, hopefully you got the idea. There's my line. And finally, let's just do one more. You can see that I have marked this up a little already. So I was using it for something else, but I'm going to start from scratch again here. Okay. Now, Z runs 1 mile per day. That's pretty cool. I wish I ran a mile every day. I do like running, actually. I don't know how many people can actually run 1 mile a day. I digress. So again, here we have a table where we don't have the number 1 for the number of days. So we're going to use our powers of deduction. We've got 1 day, which means 1 mile. Because remember, per day means 1 day. So that means 7 days is 7 miles, 14 days is 14 miles, and 21 days is 21 miles. How do we know that? Well, our rate of change is 1. So now we can plot it. And it's a little bit tricky here because we don't have a coordinate plane with those exact numbers on it, but we will figure it out. So the ordered pair 7, 7 is going to be about there, I think. Then 14, 14 would be about there. And then 21, 21 would be about there. Let's see if we can draw a line. I'll use a different color. Oh, that line wasn't too bad. And there we have it. So I will stop there. But hopefully you have a sense of what linear functions are about. And maybe you can think about other examples in real life where you might, of linear functions. There are so many. Until next time.